Hello everyone. Today we are going to talk about thermal energy. So what's the difference between thermal energy, temperature, and heat? That's the first concept we're going to go over. You might be most familiar with the word temperature, right? So temperature, you know that it's measured in degrees Celsius or degree Fahrenheit. You also know that, something that's cold usually have a lower temperature than something that is really hot. But what is hot and cold? And how is it related to what we're learning right now, which is in the energy chapter? Now, it turns out that temperature is a measurement of energy. Temperature is actually related to the measurement of the average kinetic energy of the particles inside an object. Now, I'm not talking about every single particle and all of their kinetic energy combined. I'm talking about an average kinetic energy of all the particles inside an object. So for example, you have an apple. An apple is going to have trillions and trillions of particles inside. Now, every single one of those particles, even though it looks like, it's a stationary apple, but actually those particles are shaking, right? They might not be moving around like actual movement, but they're actually shaking. They're vibrating, they're shaking. So in a sense, they actually do have movement, vibration movement, and hence they actually have kinetic energy. Now, it depends on how fast they are vibrating in a solid and how fast they are moving in a gas or liquid. They will have different type of kinetic energy. So if you remember, kinetic energy is related to speed, right? Kinetic energy, the equation for that is 1/2 mv squared, where v is the speed, so it's 1/2 m speed squared. So the faster a particle is moving, the more kinetic energy it has. So temperature is related to that. Now let's look at this animation that I have here. So what I can do is add some particle, inside this chamber. Okay, so now I have some particle inside. So on the top, you see a thermometer, and there's a temperature associated with that. So this gas right now has a temperature of 27 degrees Celsius. Now, on the upper left-hand corner, you can see the average speed. Now, that's not the speed of every single molecules inside. That's just the average. I'm showing you a graph right now. In this graph, you can see the number of particles that has a certain speed. So some particles are moving faster, some particles are moving slower. They have that kind of movement because, well, they're heated, right? So right now, the temperature is at 27 degrees Celsius. So some particles have faster speed, some particles have slower speed, and they collide with each other. They also collide with the container, the walls of the container. So some of them move faster, some of them move slower, but on average, they have an average speed. So right now, the average speed is about 460 meters per second. Now, speed is related to kinetic energy. So now I'm also showing you a kinetic energy graph. That also means that some particle moving very fast has large amount of kinetic energy, and some particle moving slower has small amount of kinetic energy. But usually, that's an average. So if you take the average speed and use 1/2 mv squared to calculate the average energy, then you get something that has to do with temperature. So for example, what happened? Look at the number of the temperature number, which is on top, and look at the average speed number, which is on the upper left-hand corner. Now I'm just going to heat it up. I'm putting a fire on the bottom, as you can see. So the temperature right now is at 100 degrees Celsius, 136 degrees Celsius. And what you can see is, well, the average speed is now higher. Okay, if I heat it up even more, the average speed will increase, and the average kinetic energy per molecule also increase. Now I can also do exactly the opposite, which is lowering. So I'm putting, let's say, put it in an ice bath. So I can lower the energy level. So I can take some energy away. And now this object has all those particles. So the number of particles are exactly the same, but they have a slower average speed. So temperature is actually just the average kinetic energy related to the average kinetic energy per molecule inside an object. So the hotter an object is, the faster its particles are moving inside on average. Okay, so it's an average value. Now, so temperature, average kinetic energy of the particle in an object. So what about thermal energy? This word actually has energy in it. Now, thermal energy, we can't really use the letter T anymore because we already use that for temperature. So thermal energy in our equation is going to be used denoted with this Q. Simple, okay? So Q for thermal energy. Okay, so thermal energy is the total. Okay, so thermal energy is the total. Okay, so total kinetic plus potential energy of every, so now we're actually counting every one of them, every particle in an object. Okay, so what's the difference between this and temperature? Well, thermal energy is the total kinetic plus potential energy of every particle in an object. Now that means the more particles you have, well, usually the more thermal energies you have. So it's the total value instead of the average kinetic energy. So for example, if you have two identical, let's say you have two identical objects, two apples, exactly the same size, right? And let's say they each have 4 particles inside, right? So they have the same number of particles. Now, and let's say the one on the left has the particle moving at these random direction quite slowly, right? And the one on the right has the particle moving at these random direction faster. So because the one on the left is slower, the particle is moving slower on average, right? So it has less kinetic energy on average. And the one on the right hand side will have more kinetic energy on average, right? So this one on the left has less average kinetic energy. The one on the right has more average kinetic energy. So the one on the left, now average kinetic energy also means so lower temperature. So less average kinetic energy means lower temperature. And the one on the right, so for example, the one on the left maybe is 10 degrees Celsius, whereas the one on the right, well, it has more average kinetic energy, which means it has higher, right, higher temperature. So maybe this one is at like 50 degrees Celsius. Okay, so that is for this simulation. So let me just turn it off. Okay, so, but for example, which contains more thermal energy? For example, a pot of boiling hot water or an iceberg. Now, an iceberg, let's say this really, really big iceberg versus a pot of hot water. Okay, so this is a pot of hot water compared to iceberg. So I do not know how to draw a pot of hot water, but that's what it is. Now, a pot of hot water has water molecules inside, but an iceberg, well, ice also has water molecules, right? I mean, water molecules in terms of ice. But think about it. Which one has more particle? Well, I would say the iceberg. Unless you have like a very small iceberg, then it's ice cube, I guess, and a very large pot of hot water. But generally speaking, you know, if you just go by logic or common sense, an iceberg contains a lot more molecules, right? So of course, which one has lower temperature? Well, the one has lower temperature obviously is iceberg. It's an iceberg, ice, right? So this one has lower temperature. Well, what does that mean? Well, that means on average, its molecule isn't moving that fast. So its molecules are, you know, vibrating, shrinking, but they are not going really fast. But there are a lot of them though. I'm not going to continue to draw this because it will take me forever. But then, the pot of hot water, I mean, all those particles are moving very fast, right? I mean, it's hot. So they all have like incredible speed, the hot particles inside. So this one will have higher temperature, of course, which because it has higher kinetic energy. But if we are asking which one has more thermal energy, now remember, thermal energy counts the total. So maybe the pot of hot water, every single molecules in there has a speed that can beat every single molecules in the iceberg. But there's simply a lot more particle in the iceberg though. So maybe for the pot of hot water, every one of them has kinetic energy of 1000. And for the iceberg, everyone only has a kinetic energy of 10. Well, but then there are like billions and billions of water molecule in the iceberg. So if you count the total, the iceberg still wins out. So for example, in this case, I think iceberg will win. Why? Because the iceberg has many more particles. right? So usually the objects that are bigger. So for example, like an elephant versus me human, right? I mean, who has more thermal energy? Or most likely the elephant, right? But if you're talking about something that is, so let's say you take two objects that are, so let's say you take two items that are similar in size, then it's really hard to say. It depends on who has, for example, if you ask me who has a better, who has more thermal energy, a horse or versus a cow, then it's really hard to tell because they're similar in size. So like particle wise, they have the same amount, I guess. But then it depends on who has the more temperature. Then in that case, right? Who has the higher temperature? Because if you have the same amount of atoms inside or similar, then the one with higher, average kinetic energy, which is higher temperature, will also have higher total energy, right? But if the two objects are very, very different in size, like a car versus like a cat, well, the cat could be a really hot cat. I don't know why a cat would be hot, but anyhow, and a really cold car, I still think the car would win because the car is simply much, 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 much bigger than a cat, right? So the total energy in a car is more than the total energy in a cat. So now the next thing we're gonna say is, well, what about heat? I did mention heat. I just talked about thermal energy and temperature. What about heat? So heat, on the other hand, heat is related to both of them, thermal energy and temperature. So we're talking about the first thing first, heat. So what is heat? Heat is the change in thermal energy. Heat is the amount of thermal energy transferred between one object to the other. So for example, when you touch a cup of hot water, so it's the amount, so let me write down the definition first. So it's the amount of thermal energy, transferred from one object to another. So for example, if you have a cup of hot water that you're holding right now, let's say you're taking notes and also drinking hot cocoa. So if you're drinking a cup of hot water right now, you can feel the heat from the cup going into your hand, right? That is the thermal energy from the cup going into your hand, and that's what we call heat. So if the cup transfer, let's say 1,000 joules of thermal energy to your hand, then that's called heat transfer. So heat is the amount of energy, thermal energy transfer from one object to another. Now we're gonna have some basic definition too from previous science class. For example, do you remember the three states of matter, right? I mean, there are more than three if you want to go really deep into that, but right now let's talk about three: solid, liquid, and gas, right? So remember the difference between them. So solid, liquid, and gas. So now let me show you this right here. So this is a solid state of water. You see those molecules, right? H2O molecules. They are not really stationary. They're actually vibrating. That's why I say they have kinetic energy, even though this is a solid right now. Now, of course, if you, so what does liquid look like? Well, liquid look like this. So now you can see those molecules are filling the container shape. Now they are not really free yet, but they are not stuck together like a solid. So now it's a solid again. So they're just vibrating, right? So in liquid, the molecule can actually slide past each other, but they are bound by gravity, so they don't have enough energy to actually break free and start flying around yet. But they could switch place with their neighbors if they want to. Unlike a solid, they're, kind of sewn in, right? Kind of like locked together. And now solid, liquid, and let's look at gas. So in gas, the molecule have so much energy that they can actually break free from each other and start like going into the air and filling the shape of the container. So this is gas form. So the only difference between solid, liquid, and gas is, well, how fast the particles are moving inside, basically. So if I take a piece of solid to begin with and I add heat, right? Let me add heat, then the solid now turns into a liquid. So if you wait a while, it turns into this liquid form, which fills the container. Now, if you heat it up even more, that liquid is going to turn into gas because some molecule is going to have enough energy to break free. And when they are free, when they have enough energy, they can actually fly, in a room randomly and, have a lot of freedom. So now these are, gaseous particle. So if I remove heat from them, I remove energy from this, I'm also removing their ability to fly around, removing the kinetic energy, which make them go slower, and they turn back into liquid. Now, so if I lower the temperature, they will turn back into liquid and then turn back into solid eventually. When they lose all their energy, they will eventually turn back into a solid. So now you can see some of the particles are, oh my god, we don't have a lot of energy, so let's stick together. We don't have energy to actually go anywhere, so now they're just solid. Okay, so the difference between solid, liquid, and gas. So let's put that in our notes. Very easy. So for example, solid, the particles are kind of, stuck together like this. So solid, right? So they can vibrate though. It's not like they can't move. They can vibrate a little bit. And then you have liquid, which now you have the particle kind of sliding. They could slide to each other. They can switch pace with labors, right? And then you should heat it up even more. So you should add heat to it, right? So every single one of these steps, you're adding heat. You're adding thermal energy, right? You're transferring thermal energy from the hot plates into your object. If you heat it up even more, if you add more thermal energy to that, you give it more kinetic energy. So now eventually they go into a gaseous form. Now they can break free. They can have like fast movement randomly in different locations. So they can move even faster around. So solid, liquid, and gas. So when a material is heated, the molecule move faster. Okay, so the molecule moves faster. The molecules move faster, and as a result, it will generally speaking, it will expand. Right? It will also expand in size. Okay, so now, so when you add energy to an object, first you raise its temperature, and then you make it change from solid to liquid, and then liquid to gas. So we call that kind of a phenomenon. If you want to graph it out, it's called a heating curve. So if an object is heated, it will do two things. It's either going to increase temperature. Okay, so it's either going to increase temperature, or it's going to perform something called like a phase change, right? So or it can change phase, change state, so from solid to liquid to gas, right? So it can either change state or increase temperature. So for example, for water, now we know that water boils water freezes at 0 degrees Celsius into solid, right? Into solid ice. And then it boils at 100 degrees Celsius. So let's plot a graph with the vertical axis as your temperature, which is measured in degrees Celsius, and the horizontal axis as the amount of energy that you add, right? So you add energy to it. If you're turning on your hot plate, that means time, because the more time you wait, the more energy is transferred from your hot plate into your object. So what happened is, what you can see is time pass is so first of all, so maybe you start with some kind of ice that's actually below 0 degrees Celsius, which is possible. And then you're going to, so at the beginning, what you notice is the temperature of the ice will be increasing, and then it reached the point where it's 0 degrees Celsius. And then what happened? Well, at 0 degrees Celsius, the ice suddenly no longer increases in temperature directly, because the ice will take that energy and melt. So you'll find that, as you add energy into the object, first the solid object goes up in temperature, but then at some point called the freezing point, the temperature increase stop and the object change from solid state to the liquid state. So at this point, we call it melting, right? So at this point, the object melts. So at the beginning, you have ice, and then at some temperature, let's say for ice is 0 degrees Celsius, the object will actually stop increasing in temperature, even though you're continuing to put energy in it, and the object just melts. Now, after all the ice melts into water, then the liquid water is going to increase in temperature again. But this time, so it will be, so right now it's going to have, so you're going to have water, right? So now it's going to be in liquid form. and the object is going to be increasing in temperature again until reach the boiling point, which for water is 100 degrees Celsius. And then you will find, oh, the temperature stopped increasing again, because now the energy is being used to change the liquid water into gas solid steam, and that we call boiling. After that, the temperature will increase again. So after you get all the liquid water into gas, which is like a steam, so into gas, which is like in our case steam, then you will find the temperature increasing again. So you get steam that are hotter and hotter and hotter and hotter. But there are certain sections of when you're heating up something, there are certain times where you don't notice the temperature increasing anymore, well, because the object is changing phase. So changing state leads from solid to liquid, from liquid to gas state, leads energy. So the temperature will increase, and then it goes into the freezing point. It will melt. So the energy is now going to be used for melting process. So you melt, and then the temperature will increase again, and then the liquid will boil into gas, and then the temperature will continue to increase again. So there are certain steps that you have to take. Okay, so now another thing that I want to review just from maybe science, previous year of science, is how does heat actually flow. So remember, we said that heat is the transfer of thermal energy from one object to another. So which way does energy actually flow? Well, you're holding that cup of hot water. Are you still holding that cup of hot cocoa? Well, if you are, then you know which way the the heat flow, right? Temperature, the heat, the energy always flow from the object with high temperature to the object with low temperature. Okay, so it's always flowing from the object with high temperature to the object with low temperature, regardless of the size. I mean, you are very big, but that cup of hot cocoa is giving you energy because it's hot, right? Because its temperature is high. So it could be like, so it's not the thermal energy that determines the flow of energy, it's the temperature that determines the flow of energy. So for example, that cup of hot cocoa, right? And you, which is like huge, gigantic human being. So, well, if you look at this, I mean, who has more thermal energy? The hot cup of tea or you? Thermal energy, remember, that's the total, right? You are so much bigger than that cup of hot cocoa. But however, which way does the energy actually flow in here? Well, it's actually flowing from the cup of hot cocoa to you. The direction of the energy flow is actually from the water to you, or from the cup of hot chocolate to you, because the cup of hot chocolate is hotter, right? Maybe it's at 90 degrees Celsius, and you as a human being are usually at like 37 degrees Celsius, right? 36, 37, 38 degrees Celsius. So it's the one with higher temperature that's the one that is sending energy to the object that has lower temperature. So it's always like that. It doesn't matter who has more thermal energy to begin with, okay? It's the temperature. Now, so what are the three ways that an object can pass you the energy? So that's a review from science class, right? So the first one is you holding the object directly, which is called conduction. Hopefully you remember that. So conduction. So this is when the object is directly in contact with you. So it needs direct contact. So the energy is transferred from the object to you by you touching it. So you can have like a small object, a bigger object. So whichever one has the higher temperature is going to transfer energy to the one with lower temperature. So for example, if the object on the left is, let's say, 30 degrees Celsius, but the object on the right is right at 0 degrees Celsius, then the direction of energy transfer is this way. It doesn't matter that the object is bigger on the other side. Okay, so energy is transferred from the higher temperature object to the lower temperature object until when? Usually, it's until a point we call thermal equilibrium. Hey, sounds like chemistry now, right? So until thermal equilibrium. That means until the two sides has pretty much the same temperature, right? Until both sides has the same temperature. So the energy is going to transfer the two object, between the two object, from the higher temperature object to the lower one, until they reach the same temperature. So this process will continue until when? Until they both reach the same temperature. And when will that be the same temperature? We don't know. It depends on the type of object. So sometimes maybe until they both reach, let's say 12 degrees Celsius. And that's when they will stop. So when they're both 12 degrees Celsius, then, the objects are no longer, they're technically still sending energy to each other, but the amount that they send and the amount that they receive will be exactly the same. So they're in equilibrium. Okay. Now, so every time you put two objects together, eventually they will be in the same temperature. That's why a cup of hot water, if you leave it on, leave it out in the oven, it's eventually going to be the room temperature, right? Because the rest of the room is at that temperature. So if you leave anything in an environment, eventually that object will have the same temperature as the environment. So for example, the reason why, so our human body temperature is about 38 degrees Celsius, right? So in a murder, for example, if you have you discover a body, you can actually use the temperature of the body, of the deceased person's body, to determine the time of death. Because if the person was killed just a minute ago, his body temperature should still be pretty hot, right? Which is our temperature right now, 38 degrees Celsius, for example. But the surrounding temperature, the air temperature surrounding us, is 10 degrees Celsius, I guess. So the longer you wait, the more the body temperature is going to approach that value, 10 at the end. So by going back and using math and physics, of course, you can actually determine the time of death of a person when you discover the body by just the body temperature itself. Okay. Now, of course, if you wait really, really long, it's going to be if you wait 5 hours, the body's going to be at room temperature. So you can no longer tell if the body was there for 5 hours or 50 hours because the temperature alone will be the same. So you have to use other techniques to determine the time of death. But what I'm trying to say is two objects together will eventually reach the same temperature. That is always true. Okay, eventually. Now the first way is conduction, transferring energy from one to another. The second one is, what is it? Convection. So this one is called convection. That's the reason why your water, moves around when you boil them. Conduction, convection. So convection depends on the movement of the particles in the fluid. So in this case, this convection works with both liquid and gas. So it could be liquid or gas, because liquid molecules can actually move around. Gas molecule can also move around. But as you've seen from that simulation earlier, right? Solid molecule can't really move around, so they can't really go up and down and give other people energy. So convection, that is another way of transferring energy. So it's the particle that is hotter. Usually, if you heat up something, it is going to move faster. That means it's going to require more space, which means it actually become less dense. And things that are less dense will rise to the top. Things that are more dense will sink to the bottom. And the cycle continues. That's how the energy is actually distributed within, for example, a bottle of, pot of water. The bottom of the water get heat up first. And as those water molecules near the bottom, which is closer to the heating elements, right, gets heat up, they expand, so they become less dense and they rise to the top. And the water near the surface of the pot is colder, so they sink to the bottom. They're denser, sink to the bottom, and now they are near the heating elements, so that they get heat up and then they rise to the top. So now you have a convection current. Now, can you actually heat up something without touching it though? Without doing conduction or convection? Yes, you can. And you have to use something special, radiation. For example, we are heated up by the sun. Earth itself is heated up by the sun, and the sun is not touching us. I mean, we'll be on fire if it was. And there's also no molecule to do heat convection between us and the sun. It's empty space. So radiation can directly heat up something. So you just need radiation. So radiation, no medium required. So, for example, the sun sends us a lot of radio wave, X wave, gamma radiations, and infrared radiation, ultraviolet radiation, and all of those radiation arise on Earth and heat us up, right? Okay, so now, okay, but here's something funny though. For example, if you go out on a winter time, no, actually, you go in the summer, you go to the beach, and you realize the water is actually a few degree cooler than the ground and the air surrounding it. Why? The sun is heating up both the ground, the air, and the water at the same time, at the same rate. Why is the water cooler, a little bit cooler than the rest of the environment? Have you ever wondered about that? Because that is actually a very cool phenomenon. It has something to do with the amount of energy that you need to heat up something. Now, it turns out that objects do not heat up equally. Okay? Some objects, some elements are easier to heat up, some are harder to heat up. So, for example, now let's look at this simulation. This last one right here. So, this simulation right here. So, for example, I can put a brick and an iron bar, and I put 2 thermometers so that you can know their temperature on top. And I will show you that they contain some amount of energy inside, and I'll link the heater so I can heat them up both at the same time. Now I'm going to turn on the heat. So now you can see the energy is transferred from the heating element into the iron. But if you look at the temperature increase, right? You see that the brick is actually reaching higher temperature faster than the iron. Can you see that? The thermometer on the brick is almost near the top. The iron bar is still going up. So it's easier to heat up brick than a piece of iron, even though you give them exactly the same amount of temperature. Now let's reset. Let's try water and iron. For example, in this case, let's put 2 thermometers, one on the water, one on the iron bar, and let's heat them up again. Oh, actually forgot to link them together. So cool, there we go, 1, 2, 3. So it should be fair. I'm sending the same amount of energy to water and the iron at the same time. But look at how fast the iron is increasing its temperature and how slowly water is increasing its temperature. So it turns out that water actually can store a lot of energy before its temperature increases. Okay, so that's one feature of water. That's really fun. And different materials store energy differently. Some material can store a lot of energy because before its temperature increases. Some material is really easy to heat up. Now, in our situation, what we have in here, so let me reset that first. There we go, and go back to the note. So the amount of energy that you heat actually follows the equation. So we can use that equation. So the equation is something like this. So thermal energy, the change in thermal energy of an object, is related to its mass and this new thing called specific heat capacity, which I'll explain a little bit later, and the change in temperature. So mc delta T, that's the equation that is on your formula sheet. Okay, so that's change in thermal energy. So the amount of energy transferred to an object is equal to, number 1, you need to know how much of an object you're actually heating up, and you need to know how much of the temperature change do you want. Do you want to change it from 0 degrees Celsius to 30 or 0 to 100? It's going to require a different amount of energy, right? So, definition. The change in Q is the change in heat. Oh, it's heat, right? It's the change in thermal energy. And it's measured in, well, energy is measured in joules, right? All the times. Doesn't matter if it's heat energy, kinetic energy, or potential energy, right? It's always measured in joules. Now, how about M? M, of course, is mass. Mass is always measured in kilogram. Okay? Now, and then let's talk about temperature first before going back up to that new thing, C. So T is change in temperature. Now, temperature is measured in degrees Celsius. So if you have a question that's in Fahrenheit, you have to change it back to degrees Celsius. So change in temperature. So usually we'll have final temperature minus initial temperature, for example. So final temperature minus initial temperature. But sometimes if you're decreasing the temperature of an object, it might be easier for you to just tell the difference, look at the difference. You should know, without the plus or minus sign, you should know what, are you adding energy in or removing energy, right? So adding energy, the change in heat should be positive. Removing energy, changing is negative. Now, so what about this C value? This thingy that's new for us. Now, this is called the specific because it's specific to each different types of material. So it's different for different types of material. Specific heat capacity. That means how much energy can the object actually hold before the temperature increase. So how much energy can the object store? And that is found on a table in your formula sheet. Now, if you go to the for Physics 11 formula sheet, right, the pink one, the very shocking pink one, right? On the back, you will find a list of value like this. So I call them the specific heat table, right? So I have copied the table on the side. Now you see, so these, the specific heat, which is C, right? So these are the C value for you. Now, so different material has different C value, specific heat value. Now these are all measured experimentally from the scientists. So for example, if you look at some common items, so for example, if you look at iron, it has a specific capacity of 425. Now what is that measured in? That is measured in joules per kilogram degree Celsius. Okay, that definition is just weird, right? So what is that unit doing? Okay, what is joules per kilogram degree Celsius? Now let's write down find some of the common items. So for example, now we just look at iron, right? 425, so we can put it down right here, 425. Now if you look for carbon, about 720. You look for copper, about 387. You look for lead, about 128. Now remember, they all have this unit called joules per kilogram degree Celsius. Now, but I do want you to look at one very, very specifically, water. Find water. So go to your table and find water. Water is right here. Now, look at the table again. See if you can find anyone that can beat water. No one. No one can beat water. Actually, another funny thing to look at is ice, water, and steam, which is just the three forms of the water molecule, basically, right? Solid, liquid, and gas actually have different specific capacity. They do. So, I mean, most of these items in here, for example, for when I say wood has a specific of 1,700, I mean solid wood. I mean, use your common sense. Like liquid wood is stupid. Or when I say air, well, okay, that's gas air, right? Not solid air. I mean, what on earth is solid air? Solid oxygen and solid nitrogen. So water has the highest specific capacity of all the material that we have naturally. It's actually sitting at this number of 4,186 joule per kilogram degree Celsius. So what is that unit? What does that unit actually mean? Now this is actually, so what is the specific capacity value? So 4,186, what is that value? That is the amount of energy that you need, right? So energy measured in joules, the amount of energy needed to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. Okay, so let's highlight these things. It's the amount of energy to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. So for example, if you look at the number for iron, 425, what does that mean? That means if you have so iron, right? So let's say you have some iron, like some iron block with you. So this is iron. Okay, so let's say you have 1 kilogram of it, right? So this is exactly, so you bought exactly 1 kilogram of iron. And its temperature, so let's say its temperature is at 39 degrees Celsius right now, and you would like it to, well, you like to heat it up so that you have this changing to 40 degrees Celsius. So let's say you want to do that. How much energy will you need? That number is the specific heat capacity. 425 joules of energy. If you add 425 joules of energy by using maybe like a heat gun, or maybe by boiling it in hot water, if you add 425 joules of energy, you will raise the temperature of 1 kilogram of iron by 1 degree Celsius. Now, some people are going to ask, what if I have like 2 kilogram of iron? Then what? Well, then double the energy. 1 kilogram, 425, 2 kilogram, 850. Just double it. What if I want to raise the temperature by 2 degrees Celsius? Double it again. So the specific capacity is a number that you need, the amount of energy in joules that you need if you have 1 kilogram of that object and you want its temperature to go up by 1 degree Celsius. So if you want the temperature to go up by 20 degrees Celsius, multiply that by 20. But then if you want the mass to heat up more than 1 kilogram, then multiply it by the same amount, right? By the amount that you want to heat it up with. So then there's something really funny then, which is if you compare water and iron, right? So water almost have 10 times the specific capacity than iron. What does that mean? It means water is 10 times more difficult to heat up. Now that is actually very amazing. The reason why we have our cooking ware, so like our frying pans or pots, are usually made of irons and copper. The reason why that is the case is because irons and coppers are easy to heat up, right? They're easy to shape and easy to heat up. It only takes 400 joules of energy to heat up iron bar by 1 degree Celsius. That's the reason why we use iron as our sometimes as our frying pans, right? Steel is basically iron. So it's easy to heat up, so we can transfer the heat from the heating element to our iron frying pans to our food, right? Now, but easy to heat up, water is a lot harder to heat up. But easy to heat up sometimes is not actually a good thing though. Now, why do we cook things in water sometimes? Well, we cook things in water because it can actually stay hot for a long time. Now, water is still pretty hard to heat up. It takes 10 times more energy than iron to heat up water. But that also means it takes 10 times more energy to make water cool down. Think about it. If you put a piece of really, really nice, let's say, a meat in an iron plant, it will actually cool down very, very quickly. But then if you keep that piece of meat in boiling hot water and you turn on the fire for both of them, of course, to be fair, the piece of meat is going to stay hot for really, really long. I mean, when is the last time you eat something like curry or maybe chili? It stays hot for a long time, right? Because the meat and the vegetable is actually in water, in the sauce, right? Which is made of water, of course, a lot of water inside. So it stays hot for really, really long. But think about it, the last time you stir fry something and you put it on a plate and put it on the table, the stir fry cools down really, really fast, right? Sometime after you finish your dinner, the curry and the chilies are still hot. They're still hot because they're in water. And water takes a lot of energy to actually cool down. So it takes a long time to cool down water. But it's really, really, really easy to cool down irons and copper. So heating up takes a lot of effort for water. But cooling it down also takes a lot of effort, which in some cases is a good thing. Now, then some people look at this table right here and they're going to ask, Mr. Chang, what about lead? Lead can heat up even faster. Why don't we use lead to make our cooking wares? Well, unfortunately, my friend, lead is poisonous. Do you really want to eat that? Eat food that are cooked with lead though, right? I mean, it's poisonous. So if you inject some lead with the food into yourself, you can get poison, lead poisoning. You're gonna die from it. So I don't think you should be cooking with lead, even though lead is very, very thermoconductive. So we use the word thermoconductive, which means it conducts heat really, really well. It heats up really well. Lead is actually not, lead is good. I think it might be the lowest on our list, but actually, if you look at it, gold is not bad too. Look at gold, 129. Gold is not poisonous. You can actually eat gold. It's not poisonous. I'm not suggesting that you go and eat your parents, gold rings right now, but you can eat a little bit of gold and it's okay. But why don't people use gold to, make their cooking wares? Because it's expensive. Like, why would you do that? It's very expensive, right? So no one usually do this. Okay, now, so we'll look at two really quick examples. So let's say I'm going to make a cup of coffee by boiling 250 grams of water that is initially at 15 degrees Celsius. How much heat is needed? So I want to bring water, 15 degrees Celsius water to boiling hot water, which is 100 degrees Celsius, right? And how much water do I have? 250 grams. In kilogram, 0.25 kilogram, right? Divide by 100. So I have everything I need. So how much heat energy do I need to transfer from my heating element to my water? Well, the change is going to be mc delta T. Now, how much is my change in temperature? My change in temperature is 100 minus 15, which is, 85 degrees Celsius, right? So that goes into here. And the mass of the water goes into here. And where is the C value? Well, that is for water. So I'm making water. I'm cooking water, boiling water. So I need the specific heat capacity for water. So every question is going to be different. Look at which material you're actually using. So in this case, for water, this number is 4186. Now, that's only for water. If the question say you're heating up, for example, silver, then it will be a different value, right? And then you use a calculator, you multiply the 0.25, 4,186 specific capacity, and the change in temperature, 85 degrees Celsius, you're going to get the amount of energy that you need to heat up that water, which is going to be 88,953, 89,000 joules. Okay, I'm skipping the calculation. You can check it with a calculator. Okay, pretty easy to use. Just need to know, make sure you know how much of the material you're heating up, what is the specific capacity from the table, and the change in temperature. So, now, next one, which is more advanced. A 35 kilogram child goes down a 3.2 meter height slide. The child initially at rest and moving at 1.8 meters per second at the bottom of the slide. If the slide is made of 12 kilogram of iron and all the heat is transferred to the slide, by how much does the temperature of the slide increase? So this is actually a pretty funny question. So you have a slide, right? And you start from the top. So you start from the top. So that's a slide. And you start from the top. And you arrive at the bottom with some kind of speed. Now, at the top, you have initial velocity of 0. At the bottom, you have a final velocity of 1.8 meters per second. And this slide right here is going, it's 3.2 meters high. Now, some of you might know what we're going to do next. Conservation of energy. I actually want to know, how fast were we supposed to go if there's no friction? And how fast is going right now is 1.8 meters per second. But that's with friction. So this question actually has friction in it. So when you're at the top, how much energy do you have at that point? Well, at the top, you're not moving. So the only energy you have is potential energy, which is calculated by mgh. 35 kilogram children, gravity, and your height, 3.2 meters. And your potential energy at the top is about 1,097.6 joules. Now, remember what we learned earlier in this chapter. If the world is perfect, then at the bottom, that should be the same amount, right? So at the bottom, you no longer have any height. You're at height equal to 0, so you only have kinetic energy. So how much kinetic energy do you have? Now, in an ideal world with no friction, that should be the same, 1,097, right? It should be the same. Is it the same? So 1/2 mass, speed, square the speed, and what do you get? 56.7. Oh my god, it's not even in the same ballpark, right? From the beginning, you have 1000 joules of energy. At the end, you're only left with 56 joules of energy. So what on earth happened to the other 950 joules of energy, right? Approximately. So what happened to the other, like, well, actually thousands of it, joules of energy that's missing? Well, that is going to be energy loss due to what? Well, due to the object rubbing against the slide, right? Due to friction. Energy loss due to friction. When you rub your hands against each other, you create heat. When you slide down the slide, you create heat. So the energy is going to be due to friction. So the missing energy is turning into heat. So the missing energy is all converting into thermal energy. And let's say those thermal energy is there to heat up, it's only heating up the slide instead of heating up you. And then we can find out how much of the, so what is the missing energy? So the difference between them, right? So 1097.6 minus 56.7, which is going to be the missing energy part, which is about roughly, right? I mean, let's do roughly right now. 1041 joules of energy missing. So what happened to that? Now we're going to assume it. Now in real life, what happened is some of those energy is heating up the slide that you're sliding down with, the iron, and some of those energy is actually heating up your butt, I guess, because your butt is rubbing against the iron, right? So it's actually heating up both objects. But now let's assume that you're not taking any energy, and let's make it simple. Only the iron slide is actually absorbing the energy. So the heat is heating up the iron slide. Okay, so now to find out how much will be the temperature change on the slide, we use the thermal energy equation. So how much thermal energy equation is transferred is going to be 1041 joules of thermal energy. How much iron are we trying to heat up? 12 kilogram of it. What is the specific heat capacity for iron? That we have to go back to the table, and we find iron 425 joules of, okay, so 425 joules. And what about the change in temperature? That's exactly what we're looking for. So we're actually trying to find out what the change in temperature is. So we don't have that value right now. We're trying to look for it. Okay, so use your algebra. 1041 divided by 12 divided by the 400 and something, and you get the change in temperature, which is positive 0.2 degrees Celsius. So that means every time a kid slide down the slide in our hypothetical question, the iron slide is actually going to increase its temperature by a little bit, by 0.2 degrees Celsius. So if a lot of kids are lining up to do this, the last person is going to be sitting on a very, very warm iron slide. And that's actually some of the reason why I think when I was younger, a lot of you maybe also have experienced that if you go down the slide wearing shorts, sometimes you get like a burn, right? Like a friction burn at the end, because you're sliding down and then the friction is rubbing your thigh against the iron bar because you're wearing shorts, right? So there's some skin that's actually in contact with the iron bar, and you're going down like that, and by the time you go down, the temperature, the energy is going to be heating up both your leg and also the iron bar, so you feel like really hot, and sometimes you get a burn from that. Okay, so today this is a long lesson. I hope you did take a break in the middle. I will mention in the description that you should take a break in the middle. And so the homework is going to be on the worksheet. So the worksheet is actually at the end, I think, of the package. But don't do all the question. Only do question 1, 2, and 4 for now. 1, 2, 4, not 1, 2, 3. Okay, 1, 2, 4. I will mention it in the description of the task for this week. Okay, so 1, 2, 4. You have the answer on the bottom, also up here. And see you next week. Goodbye.